Hi, everyone. This is Dr. Lovell, and we will be talking today about descriptive statistics and especially measures of centrality and dispersion. So, this will cover the first kind of 3 weeks worth of statistics. Um, Really, it's just kind of basically getting us familiar with how variables work, how to understand the spread of variables, and how to kind of compare them. So, let's get started with the different types of variables. So there are two types. Okay, before we get into the types of variables, there are two types of statistics in this class. There's descriptive, which are statistics that are simply describing a variable or measuring the association between them, but you're really talking about exactly the data that you have. So this includes percentages, averages, and counts. And then I have a couple of things that we're going to be learning later on in the course, like ANOVA, chi-squared tests, and regression. Then there are inferential statistics. This is when you have a sample and you're making inferences, meaning estimations about an entire population. So because with the sample, you can rarely survey an entire population, right? So let's say if we were trying to understand the voting behaviors of all white men in the US, that would be really difficult to find all men in the white men in the US and ask them questions. So instead, they will take a sample and then make estimations about the full population. And so that's what we'll be doing a little bit later, is inferential statistics. Okay, so within all of this, I just wanted to bring that out to describe, like, this is what we're doing first is descriptive statistics, and then we'll move into inferential statistics. But regardless, the way we do variables are important for every single kind of statistic. So there are three main kinds of categorical variables we're going to talk about. The first is nominal. These are variables in which the categories of those variables can't be compared to other categories. So it's kind of like gender, race, favorite color, your country of origin, right? You can't say that in Zambia is more than Korea. That doesn't make any sense. You can't say that being liking orange is more or less than liking yellow. That again, that doesn't make sense. So that's what makes them a nominal variable is that they're just comparable as discrete categories that have no relation to each other in terms of more than or less than. For the next kind, it is a type of nominal variable. It's called binary, and it's a variable that has two all-inclusive categories. So generally, people would use gender as like the classic binary variable. We know that gender is not binary. We know that it's more than that, but most surveys still only ask people if they're male or female, and so it's often treated as a binary variable. But we will often create binary variables out of other categorical variables, and this will make sense later on when we're doing the statistics. But let's say we have a race variable that has four categories: white, black, Latino, other. What we would do is make four binary variables, one that, a white variable, which we would code 1 for everyone who is white and 0 for everyone who is not white. So it still includes all of the people in the sample, but it's coded as two possible categories, right? So we could do the same with black, Latino, and other. Is code for 1 for the thing that we want to talk about, so the black population, and then 0 for everyone else. Okay, so that's called a binary variable. Okay, the third type of categorical variable is ordinal. These are categorical variables that are still categories. They're not numbers, but they can be ranked. So they have some certain type of order. And so there's a couple of examples I put here. Class is one of the most famous ones. If people like designated the class that they feel they are a part of. Working class is lower than middle class, but upper class is higher than middle class, right? So you have an order to these. It makes sense that some are more than or less than others. So we have education. You could also say happy, like a lot of the psychological self-assessment tests are ordinal variables when they say from 1 to 5, 5 being very happy and 1 being not happy at all, rate your happiness level. Right? Those would be ordinal variables. And one thing to note, while we may know the order of the categories, we know that an A and a B is better than a C and a D, we can never know the distance between them. Like, we can never evaluate how much work does it take to get from a B to an A, or how much happiness is, what's the difference in happiness between very happy and somewhat happy? We can know that one is more than the other, but not by how much. So that's one of the big drawbacks of ordinal variables. Okay, now there are two types of what we call interval ratio variables. These are variables with numbers instead of categories. So each number itself is a category, and there are two types. There's discrete, and this means that the numbers can't be subdivided. So like, for example, we have number of children. You can't subdivide children, meaning you can't, someone should not be able to report, I have 2.3 children on a survey. I would be worried about that third of a child, right? And you can't subdivide, number of cars on the road or things like that. So it's number of categories that can't be subdivided. The whole number itself is the most basic unit that's possible. The next is continuous variables. These are numeric categories that can be subdivided infinitely. So for age, we can break that down from I am, 22 years old to I am actually 21 years old and a half, or I am 21 years old, 532 years old. So it can keep being divided. Same with income, GPA, height. So any of these variables that can be divided and it still makes sense what it is, then that is a variable that is continuous rather than discrete. Okay, so those are the 5 main types of variables we'll be using in the course in terms of how they are coded, either categorical or interval ratio. Now let's talk about how we then report the basic structure of the statistics we're using of the population. So here are what we're going to go over. For every variable, you can present these as frequencies or counts, percentages, proportions, ratios, rates, and percentage change. Percentage change is something that's not necessarily contained within itself, but we'll talk about that in a second. So the most basic thing to do with a variable is count the number of cases or observations, right? So here we have the variable religion in the Chicago metro area. And for each category, you see in the table, there's evangelical, mainline Protestant, Black Protestant, Catholic, other Christian, Jewish, et cetera, et cetera, et cetera. For each category is listed a number. So for evangelicals, there's 139 out of the 867. So that 139 is the frequency of evangelicals in this data set. We also might just call them cases or counts because you're literally just counting each case that falls within that category. So that is the frequency. A percentage is providing the frequency of a particular category compared to all of the cases within that variable. So that is a really complicated term for something we already intuitively know. So it's seeing what is the percent of evangelicals in the total population of the Chicago metro area, right? And so the equation for that is taking the frequency divided by the total number of cases. So in this case, it would be, for Catholic, it would be taking 295 and dividing it by 867. And then to get the percentage, you multiply it by 100. So in this case, 34% of Chicago is Catholic. So to find a percentage, you take the frequency of that category and divide it by the total number of cases in the full variable. Proportions are similar to percentages, except that you don't divide or you don't multiply by 100. You simply take the frequency and divide it by the total n. So for the unaffiliated category is 191 persons in this study, divided by 867 total. And instead of multiplying it by 100, we would just say the proportion is 0.22. The proportions should always add up to 1, just like the percentages should always add up to 100. There's not really a definite reason to use proportions or percentages. A lot of places will use both, even though you can see that it says the same thing. I would argue that the general population best understands percentages, and for a variety of reasons, you'll often see statisticians and scientists staying with the proportions, possibly just to avoid that extra step of multiplying it by 100, because a lot of times when you go back to using, like comparing, you'll have to go back to proportions. So I think that's why statisticians often will report the proportions rather than the percentages. But it doesn't necessarily matter. They're telling you the same thing. Next, we have ratios. This is how you compare multiple categories within a variable. So you would take, for example, maybe you want to compare how many Muslims there are in Chicago versus how many Buddhists. And then this is what ratio is comparing those relative sizes within the population. So let's say we're comparing the number of Catholics to evangelicals. All you're doing is taking the first category you're interested in and dividing it by the frequency of the second category. So here we have Catholics are 295 and evangelicals there are 139 in this data set. So that gives us a ratio of 2.12. And the way you talk about this is the ratio of Catholics to evangelicals in Chicago is 2.12, or you could say for every one evangelical there are 2.12 Catholics in Chicago. Okay, so that's how you understand a ratio. Is the top number is how many the ratio is how many of the category 1 you have for every single category 2. So for one evangelical, there are 2.12 Catholics in Chicago. Rates. This is often used in epidemiology, but it's the number of actual occurrences of a situation or an event divided by the number of possible occurrences. The reason this is often used in epidemiology is because the total population is the possible infections, right? So if we're thinking about the entire US during COVID, we would think the possible infections would be every single person. And then the total infections would be the amount of actual people infected. Now we know that, especially with COVID, people are getting infected twice, even more, so it's hard to say what the possible occurrence is. But if we just assume that everyone could only get infected once, that would mean the possible infection for COVID would be 330 million. That's the population of the US. And then the total cases, I actually updated this, so it's no longer December 21st. This is recent. So this is like total cases as of whatever week this is, January 29th, 2022. So there's been about 73 million, probably more, but that's what the, official counts are saying. And so the rate comes out to be 0.22. Now, it doesn't often make sense if you leave it as 0.22, because the way you read rates are for every one person, 0.22 will be infected. And that doesn't make much sense. And so usually they'll multiply the number by either 100, 1,000, 1,000,000, depending on how wide their data set is. So I think it makes sense to do it by 1,000. So we would multiply 0.22 by 1,000 and say for every 1,000 people, 222 people have been infected. Okay, so that is how you do a rate. Next, this is how we present data is in a frequency distribution. So a frequency distribution is just a table that is reporting the number of cases for each category of that variable. This is simple for nominal and ordinal variables because you take each category and you provide the frequency for each category. When you have something like an interval ratio variable, like age, you'll, instead of reporting how many cases are for every age, right? That would be a super long table with you counting how many people who are just born, how many 1-year-olds, how many 2-year-olds, how many 3-year-olds, etc. So often they will group those values together and count. So they'll group all people in this data set that are between 0 and 10 years old, and this is how many there are. 11 to 20-year-olds, this is how many there are, okay? But we'll be seeing a lot of frequency distributions throughout the semester and even in this presentation. I wanted to show you the frequency distribution before doing this calculation, but this is percent change, often shown as percent delta. Delta is that triangle. So percent delta, oh, it went forward, is percentage change. So if you ever see percentage triangle, that's what it means, is calculate the percentage change. What the percent change is the amount to which a variable has increased or decreased over time. So this is always when you have a time variable like we have here with the different months of 2020 and how many cases occurred that month. And so what you do is you pick the time 2 that you're interested in, subtract it by time 1, and divide it by time 1. And when I say time, it says frequency of time 2, so you would take the number of cases for that time minus the number of cases for time 1 divided by the number of cases for time 1. So if you can do a percentage change just of cases, but I wanted to get a little bit more complicated and do a percentage change of COVID rates. That means we have to calculate the rates of the months before we do the percentage change. So let's do the October rate and the November rate, and then see what was the percent change of the rate between October and November. So if you remember from earlier, a rate is the infections, like the total actual infections divided by the possible infections. So since these are Chicago's COVID cases, the total possible infections would be the population of Chicago, which I have there, and the October infections are 26,300. So we take that divided by the total population of Chicago, and we get 0.0098. Since we're doing a percentage change, we don't really need to multiply that by 1,000 to get a better, description to be able to describe it better to the public. We can just stick with 0.0098 for now. For the November rate, we have to do the same thing, but use November infections. We see that in November, it jumped to 56,000. And so we divide that by the Chicago population, and the November infection rate was 0.021. Okay, so now we have our two rates, and we can do this for the percentage time. So at the top, that formula, instead of the frequency of time 2 and time 1, we'll do the rate of time 2 and time 1. So percentage change in rates would be the November rate of infection minus the October rate divided by the October rate. And I have that in the final equation down on the bottom. We multiply that by 100 to get the percentage change, and we have a percentage change of the rate as 116.2%. So the infection rate increased by 116. Now, a quick just kind of suggestion to remember, when you're working with percentage change, if there was a 0% change, that doesn't mean it went to 0, that means it stayed the same. So if there is a 0% change, you have the same frequency or the same rate between the two times. If it's 100% change, that means it doubled. So it would be 100 means times 2. If it's negative 100, that means it halved. So those are some really great cheat-like ways of thinking about it to know what a percentage change means. Is that if it's 100% percentage change, that means it doubled. If it's a 0% change, that means it stayed the same. If it's a negative 100%, that means it halved. It was divided by 2. Oftentimes in a frequency distribution, you'll see cumulative frequency and cumulative percent. That just means that as you list the different categories in a frequency distribution, instead of showing the single count for each one like you see in that first column, so March is 4413, April is 21566, instead of just listing how much, you're listing the frequency of that category plus every single frequency before that. So for March in cumulative frequency, we have 4413, and then we add April's plus March's to get 25,979. And then we add May's to all of that, right? So it just keeps getting bigger and bigger and bigger and bigger and bigger. And then finally, when you add November's, this is the total number of cases between March and November. That's what a cumulative frequency does. And the same thing with cumulative percents is you're just counting the percent of each cumulative frequency to the final total. And so you'll see that this cumulative percentage keeps growing until we have 100%. That means 100% of the cases we're from November to March, right? It would be saying in September, we hit almost half of the total cases to March by September. And that means another half was between October and November. So we had half the cases in 2020 between October and November. That's why cumulative percentages are helpful. Okay, now we're going to get into the real meat of what descriptive statistics is doing. A lot of descriptive statistics is measuring the central tendency and the dispersion of a certain variable. And we'll talk about what this means, but essentially central tendency is talking about where do we see the most cases within a variable, which categories, which numbers do they kind of group around the most, and dispersion is looking at how do they spread? How different are the cases within a variable? So before we get started, I wanted to show you, we talked about frequency distributions in terms of the table, and you see that on the left, but you can also do a frequency distribution in a graph. Here, those are called histograms, is when you see the bars stacked of the frequency of a single variable. So on the left we have this is just a fake data set I created that we would have, the number of students in a class and their ages. So 3 students who are between 21 and 30, this is a totally fake fake set of numbers, but we would see them then plotted, the count of students on the right with the 84 in between 81 and 90. So oftentimes we will see the histogram curved out, and that is called a frequency curve. And here's just an example of what that would look like. Okay, so when we're describing a frequency distribution center, what we're talking about is measuring the mean, median, and mode. These are all measurements that measure the center of the distribution. And it's easy. The reason why I introduced the frequency curve is because it's easier to see what we mean by mode, median, and mean when we're using that curve. But this is kind of another way of thinking it is of thinking the center of gravity of this distribution. Where is it pulling into? And like I said, the dispersion is looking at the range, right? And the variable's distribution throughout the numbers and throughout the categories. One of those measurements is the range. But here are the different kinds of central tendency and dispersion. So the central tendency is describing the average or the center, whereas the dispersion is looking at how it spreads throughout the possible categories. Let's start with central tendency. So the mode and the median. The mode is simply the most frequently occurring value in a variable's distribution. That means a certain value has to occur at least twice. Sometimes there isn't one that exists, right? It might mean that there is no single value that occurs twice in a distribution. Sometimes there are many modes. That would mean that there are multiple values that are repeated the same amount of times. So let's say you had, if you have an age distribution and you have 20 people who are 16, 20 people who are 35, and 20 people who are 81, you would have 3 modes, 16, 35, and 81. The mean, or the median, is the value at the exact center, meaning you listed all of the values and you found the one value that 50% of them are below and 50% of them are above. If you have an odd number of values, that means the median is the exact middle number because it would have an equal number on either side. Or if you have an even number of values, you take the two middle ones and you divide them by 2. You take the halfway point between them. So pause this, or wait, first, I'm going to ask you to look at the modes and medians. It's easier to do that when you rearrange it in order of values, so we're going to rearrange them here. You have the lowest values at the bottom and the highest values at the top. So pause the recording right now and try to determine what are the medians and the modes of the hours at work and the hours on homework. Hopefully you paused it because I'm going to give the answer. For the hours at work, the median is 33. We see that because since this is an even number, we have to take the two middle values, that's 5 and 6, and we add them up and divide them by 2 to find the midpoint between them, and thankfully 33 times 2 divided by 2 is 33. So the reason why it's the median is because there are 4 values before 5 and 6 and 4 values after 5 and 6. So it's right there. Those two are the middle. The mode is also 33 because there are 2 33s and no other value is repeated. So that means 33 is the most repeated value. For hours on homework, there is no mode because none of the values are repeated. However, the median, which again, we take the number 5 position divided by, plus the number 6 position divided by 2, because there's 4 before, 4 after, and so that's 19 plus 21 divided by 2, which gives us a median of 20. If you didn't get the same answers that I did, go back and look at the calculations for mode and median up here and see how I did it. For the mean is the arithmetic, I don't know how you say that, average of a distribution. We're going to need to get familiar with the ways these are written out. Even though you all know what a mean is, it's simply the average. You add everything up and you divide it by the total number. But these symbols will become more important when we get to more complex statistics, so make sure you get familiar with them now. X bar simply means the mean of a variable. So remember, X bar is the mean. And then when you have the sigma, that is, you add all of the cases up. So, and then X of I simply means every single case, that you would take the first case, the second case. When you see that I, it simply means take every single case of that and repeat it. So this is saying add all of the X values together and then divide them by N. That's exactly what you're doing with an average, is you're adding up all the values and you're dividing it by the total number of cases. And this is just the statistical notation for describing that. So you have, I'll read it to you. X bar is equal to the sigma of X of I divided by N. So sigma just means you add up everything repeated within its parentheses, and X of I is telling you what to repeat. So if we go back to our mini data set, how would you find the mean for hours of work and hours on homework? Pause this and try to figure it out for yourself. Hopefully you paused. So remember, you would add all of these up and you would divide it by 10 because that's the number of students. So the hours at work mean is 32.7 and the hours on homework mean is 21. If you didn't get those, go back to the previous slide and make sure you understand how to calculate the mean. So let's talk about some of the characteristics of the mean, because that's what's important here in terms of statistical analysis. So the mean balances the scores. So here we have the, if you take every case and every value of that case and you subtract it by the mean and then add them all up, it balances those scores and you'll come out to 0. So this is kind of weird of what that's kind of trying to say. But so essentially you're looking at how far from the mean is every single value. And if you take each value's distance from the mean, that means the mean is the exact center. So let's see what that looks like. Okay, so here is the mean, this blue line. And if you take everything below it and add it up, and you take everything above it and add it up, they will equal out. And so when you subtract it from the mean, it becomes 0. So everything before and after the mean's position are evenly weighted. And although there are more boxes to the right of the mean, there are more cases and boxes to the left of the mean. So the second characteristic is that it minimizes variation. So variation is the distance a case is from the mean squared. So it takes what we did here by adding up all the distances from the mean, and it's squaring each difference. And the reason why you square each difference is because it takes away those negatives. Remember, a negative squared is always a positive. So when we take the squared of each case minus the mean, it means we won't be coming up with 0. We'll be creating a forever, positive thing. That's hard to describe. So in the previous table, when we did 10 minus 32.5, we came up with negative 22.7. But here, if you do, when you do 10 minus 32.5 squared, you get a positive number. So let's take hours at work. For student 1, the mean is 32.7. And so we take the value, 35 minus 32.7, and then we square it, and that gives us 5.29. Whereas student number 2, 30 is below the mean of 32.7. So we take 30 minus 32.7, square it, and we come up with a positive number. And so when we add all of these together, remember that's what we're doing because of the sigma, when we add all of the variables, the variation away from the mean is 1,788. Now that might not mean much, but what it's saying is this is the total variation away from the mean that each of these values hits, okay? And the reason the mean is important is it minimizes the variation between all of these cases. If we picked either the mode or the median and saw how far away each case was from those, the number would be higher than this number. So the mean it minimizes the variation away from that central point. Okay. This is an example of me using the median, which is instead of the mean. But here the sum of variations is slightly larger. So here it's 1788. But when I switch all these calculations with the median, 33, it grows a little bit, right? 33 isn't too much bigger than 32.7. That's why it's not much of a difference. But it is larger. And so this whole process of minimizing variation is called the least squares principle. So the reason that xi minus x bar is squared is to make them all positive. And this becomes, by squaring each outcome before you add them together, you can see the total variation. And this becomes very important later when we're doing regression, because regression is a way of evaluating which variables have the most influence on each other. And so you want to see how much variation is occurring between variables. And that will all make sense later. Just know that using the mean is important for minimizing variation. However, the mean can also be misleading. So the reason why is because it is the most affected by outliers. So if we're taking, here in this random sample R data set, the mean is 5.998. While the median is 6, so it's fairly close. We can also see here that the mode is 6. The mean is being pulled to the left because of all of those really far left categories, whereas the median is staying constant. Here we have something that's a little more dramatic. If the median is 44, the mode is going to be somewhere around 35, and the mean is 46.8, so it's being pulled to the right by all of these far right categories. This is called skew, is when it's being skewed towards a certain side. So whenever this side that I don't know if you can see me like falling to the right, but these high cases to the right are really pulling that mean to the right. So it might not, so the mean is being pulled away, and that means the median stays relatively stable when you have a skewed data set, when you have values pulling the mean to the right or to the left. And so when this is happening, it's often important to show both the median and the mean, so it tells your audience how the distribution is set. I'm going to skip this if you want to go look at, so I added, I guess I won't skip it. So in this, remember before we had 10 students, I added an 11th student with really extreme values. So 65 hours at work is far higher than the rest, and 12 hours on homework is far lower than the rest. And I'm showing you how it changes the median less than the mean. So the mean here changes from 32.7 for hours at work to 35.6. So it grows quite a bit, whereas the median stays the same. And they'll let you do the work to kind of see how that happens. For hours at school, when you add in a really low value, it takes down the mean, and it takes by more than it's taking down the median. Okay. I usually do this with people who are in class, so if you're interested, we can pull this up in class and do it together, but it would be a good idea to pause for a second and think, based on what you know about the U.S. income inequality, which is skewed to the high end, right, to these really small but wealthy people, do you expect the mean or the median to be higher in the U.S.? Or do you expect the mean family income in the U.S. is higher or lower than the median? And here I have some links that you can go to kind of see why it's important to understand the mean and the median in the U.S. income rates. Okay. We're going to go through income or measures of dispersion. This one gets a little statistical because the reason why we use these different measures is based on stats. If you are confused, that's okay. Make sure you know just the definition of each of these dispersions. Okay, so the first is the range. The range is simply the highest value minus the lowest value. And that gives you the spread of all the possible values are contained within this range. So here for year 2015, it looks like the highest value is around 90 and the lowest is around 16. That would mean its range is around 74, whereas for year 2000, it's going to be around, 40. So we can see if with that measurement, we can see that year 2015 has a wider range than year 2000. But range can be deceptive. All three of these have the same range. Even though they're vastly different graphs of the distribution. And so that's why you would also want other measures of range and of central tendency, right, where it's grouping. So some statisticians have tried to improve upon the dispersion range by talking about interquartile ranges. What this is doing is it's splitting your distribution up into 3 equal categories of the amount of people within each category, right? So here, remember that this y-axis is counts. And so here we're doing quartile 1 is a quarter of all the cases in this variable. quartile 2 is a quarter, quartile 3 is a quarter of all the cases, and quartile 4 is all the cases. And so to find the interquartile range, you need to find the lowest value, the median, the highest value, and then the value between the lowest and the median, which is the 25% level. So you could take the median, divide by the median minus the lowest value and divide it by 2. And then you need to take the value between the highest and the median, which is the median, or the highest value minus the median divided by 2. And then so the interquartile range is simply Q3 minus Q2. And so that gives you the median, or the middle 50% range is what the interquartile range is telling us. So it's giving us the range of this middle here. Now, the problem is A and B would still have similar interquartile ranges because that 50% is still fairly similar, even though for A, a lot of it is concentrated in the middle. Within the 50%, they're still right there. C would probably be pretty different. So the limits of Q is it still doesn't show us, it still doesn't incorporate all of the data set in its range. So one thing that people have done is using deviation as a way of describing, the spread of a variable. Remember, deviation is the distance any case is from the mean. So if we have the mean here, we have a single case, x of I, we're looking at what is that deviation. These graphs might help you make sense of what we talked about before with the mean as reducing variation and the least amount of deviation. This might help a little bit. So if you want to go back to that area using this graph. But this is what a deviation is it shows the difference between a single case and the mean. Now, that only gives us one value. And we want a measurement that's describing the dispersion throughout a variable, and so that's when we bring in sigma. So we add up all of the deviations. So that's the sum of deviations. The problem is, if you have, with the mean, remember, what's it called? Because it's the absolute value in the middle, when you do this, it's going to equal 0. So we have an example here of a case on the right and a case on the left that are exactly, symmetrical to the mean. And when you take this, I have the little equations on the side, x1 minus x bar and x2 minus x bar, and you add them together, you get 0. So the problem with the sum of deviations is that it will always be 0, no matter what. If you're using the mean in a distribution, it will always be 0. That's because the mean is the center of gravity, and the left and the right sides will always even out. And that's what the sum of deviations does, is it's seeing where something is, like what's the center of gravity. So how do we add the deviances? If understanding how the distribution deviates from the mean, how do we add those together without it equaling 0? And we do that with the sum of squared deviations. This is kind of what we talked about earlier. So here's how it works. So again, we want to take the difference between each of these cases and the mean, but then instead of just adding those differences together, we square them first. So here we have 5. So 65 minus 60 is 5. Squared is 25. 55 minus 60 is negative 5. Squared is also 25, so eliminates those negatives. And then the sum of squared deviations is 50. But there's still a little problem. Because it's an additive function, meaning you're just adding the different numbers, if a data set is larger, then it ends up looking like it has more variance simply because you're adding more cases. You're adding more of these values. The more cases you have, the more variance it will seem like it has. So I'll show you how this is a problem. So let's take this is a made-up data set that I did But it's a small data set. There's only 36 people. Let's find out the deviation, the deviance for each of these cases, the deviance squared, and then the sum of the squares. So remember, the deviance for each case is taking the value, so that would be the GPA, subtracting it from the mean, or subtracting the mean from that value. So here we have 4.0 minus 2.89, and that means the deviance of those values are 1.11. When we square it, that gets us into positive territory. Remember, we want to square it so that it's not always just canceling each other out. So here we have the deviance squared for each of those values. 1.11 squared is only 1.23, etc. And then we want to add them all up. So I here have them added. First I multiply them by each of the n. So we see here this is the deviance squared multiplied by 10, because that would be adding up every single case of a 4.0 GPA. So 1.23 plus 1.23 plus 1.23. I simplify it by just multiplying it by the n. And we do that for each of these, right? So the deviance squared for 3.0 is multiplied by 15. And then I add up all of these together to get our sum of squared deviance. So for this, the sum of squared deviance for this data set is 25.51, or 29.51. If you're confused, pause it, kind of work through the math of how to get the deviance squared, and the sum of deviance squared. Now let's take a large data set. So here I simply multiplied every n by 10. So instead of 10 4.0s, 15 3.0s, we have 100 4.0s, 150 4.0s. And I want you to see that the deviance is the same for each of these. And the deviance squared is also the same, right? 1.11 and 1.23 for each of these, 0.11, 0.012. Those are all the same. But when you add them all up, because you're adding up so many more, it looks like the sum of squared deviance for the large data set is way more, 295, than 29.5. So using the sum of squared deviance really just makes it look like bigger data sets have more variance, when in fact they have the same amount of variance. Okay, so this is, here's a just side-by-side comparison. So 29.5 to 295.1. So one solution to the sum of squared deviance is called variance, which is standardizing the sum of squared deviations. To do this, you divide your sum of squared deviations divided by the total number of cases. So here, remember, our sum of squared deviance was 29.51, and we're going to divide it by 36. And that gives us 0.8197. That's our variance. For the larger distribution, we have, remember, sum of squared deviance, 295.1. We divide that by the n, the total n, which is 360, and we find that the variance is actually the same. So it's 0.8197. So getting the variance normalizes the deviance scores, right? It helps us compare data sets with different numbers of cases, and shows that the variance, it gives us a better understanding of the variance. So this helps us see that these two data sets, even though the one on the left is way smaller than the one on the right, they still vary about the mean the same way. However, one thing we've neglected so far is looking at the units. So deviation and the sum of deviations keep the units. So this is something we haven't been talking about, but when we've done, x1 minus x bar, we should have been saying that is a difference of 5 years. That's what I mean by unit. When we do the sum, it's 0 years. When we do the sum of squares, it's 50 years squared. And when we do the variance, it's 25 years squared. But that doesn't really make much intuitive sense to say, what does it mean to deviate by years squared, right? So these, in the variable age, it is dispersed by a measure of 25 years squared. That doesn't mean much. So we want to take that away. And that's what we do with what's called the standard deviation. It is taking out that squared part so we can talk about the variance in terms of actual units. Okay, so to get the standard deviation, we simply take the square root of the variance. So it's taking, if the variance is 25, then we take the square root of that. So the square root of 25 is 5 years, which is the standard deviation of x bar. So that means the average case is deviating from the center by 5 years. That gives us a good concept of how this data set is actually dispersed throughout the distribution. So let's find the standard deviation of our data sets here. Remember, we are just taking the square root of the variance. We found the variance last time. That's what s squared is the variance. Take the square root of that, and our s, or our standard deviation, is 0.905. And the way you interpret a standard deviation is by saying the average deviation from the mean for a single case is 0.905 grade points, right? It makes a lot more sense than saying 0.8197 grade points squared. Okay, so this is what happens when you have different means and different standard deviations. As you see on the left is a mean of 50. The red line is the mean of 50 with a standard deviation of 10. And then the blue line is a mean of 50 but a standard deviation of 5. So that means they both have the same mean, but because they have different standard deviations, which is measuring the spread throughout, you see that the blue line is more like shrunken up, whereas the red line is a little bit more dispersed. If you're interested, I have a website where you can go and play with different means and standard deviations to see how it changes the different distributions. Okay, so the last slide is simply a list of all of the different measurements we use for deviation, and of dispersion, and you can go through and make sure you understand each of the different types of, types of deviation, types of variance. But you don't need to know the equations for any of them except for standard deviation. You just need to know, why can't we use them except for standard deviation? What's the problem? But otherwise know that the standard deviation. So I know this was a lot to cover in 1 hour. Feel free to go back. All of these concepts are also talked about in your book, and we can bring them up and discuss them in terms of, or during class time. But I know I went through them a little fast, so I'm also putting up the PowerPoint so that you can go through slower and make sure you understand step by step how I got everywhere. Let me know if you have any questions. Thank you.